Okay, so this lecture is about mass, and in particular we want to answer the question, what is mass, and see if we can do that. So in order for us to do that, we need to have a look at what stuff is made of. Mass is often described as stuff, and it's probably worthwhile looking then at first at what this stuff actually is. So probably I'll be preaching to the converted. However, most people will know this, but just in case you're new to this, then I'll go through it. Okay, so the board's got some pretty picture over there and a few things to say. Let's see if I can't go through it. So maybe if I stand on this side and point over there, then we'll go through this bit first. So this is lecture 1, and the question is, what is mass? So first of all, I think it's useful to have a look at the atomic model, which was proposed by people like Bohr, Niels Bohr, and others, really much earlier in the piece. And it's been pretty much confirmed ever since. So it's not like this was something just dreamt up. Much experimentation has been done to verify this model. Okay, however, that said, there's still a lot more work to be done. But suffice to say that the model is useful, and in fact we use it quite a lot in industry, for instance, and its predictability is amazing. All right, so let's have a look at it. First of all, the model says that that everything is made out of atoms, if you like, at its basic level. We could argue that things can get even smaller than atoms, like for instance, we could decide what is inside the nucleus of an atom. What does that constitute of? However, we're not going to go that far. Now, what we're going to look at though is this model. So first of all, the three major components of an atom. That is the protons and the neutrons, which make up the nucleus. So let's think about the nucleus as being the central part of an atom, okay, which constitutes most of what the stuff is. So most of the stuff, if you like, is concentrated in this nucleus, okay. So I've tried to depict here the nucleus in its three components with those colours. So red would represent the nucleus, the neutrons would be represented by the green colour, and the electrons will be represented by the black colour. So if you imagine that, obviously not to scale, because the electrons will be much smaller than the protons. Okay, the other thing about this model, it says that the protons are positively charged. So we arbitrarily give things a charge, a signification like positive, and something that's opposite that and behaves in a different way, in an opposite sort of way. We call that negative. So protons will be referred to as positive. People generally understand what that means. You have a positive and a negative part of a battery, and the reason is because the direction in which electrons move, okay, to create electricity. Okay, so we've got positive charges for the neutrons, and the neutrons are neutral.
Oh, sorry, Phil.
In the video. It's okay.
It's alright.
All right. Okay, so the neutrons are neutral. Okay. Sorry, that was just a little bit of an interruption there, but never mind. That's happened. I've been poking around because I asked her to get down, and so that she wouldn't be part of the video. All right. Anyway, she chose not to come in the room. Now, I digress. The electrons are negatively charged, but they're infinitely smaller than the protons. I don't mean infinite as in, an infinitesimal, but very, very, very small compared to the protons and the neutrons. In other words, a very insignificant amount of the stuff is invested in the electron. Okay, so now the other thing about it is, where are these things at any one time, which is a really good question. Okay, so first of all, in Bohr's model, we discussed the protons, the nucleus, that's the protons, and the neutrons as being in the center, if you like, of the atom. And then around that nucleus, we have an electron that flies around it. Now, the probability of where that electron is at any time, or these electrons are at any time, okay, can be worked out. And it turns out that the highest probability, for instance, of an electron, an atom like this, which we would call that, say, hydrogen, because it's got one proton and one electron, so this is normal hydrogen, the highest probability would be that it would be at a given radius around the nucleus. So what's being depicted here is that it could actually be anywhere in this space. Okay, so there's this space around the nucleus, and within this space, this particular electron could be anywhere. If you want to have a look further at that sort of thing, probably if you look at Heisenberg's uncertainty principle, have a look at that, look that up, and it'll probably give you a better understanding of that. But I will get on to Heisenberg uncertainty principle a bit later. Okay, so not in this lecture, but in further lectures, because it's a very, very interesting thing where we can know where something is, but at that point we can't know, for instance, what its wavelength is, and vice versa. Okay, you need to go under if you want to come through here. Okay, all right, now let's have a look at, summarize what we're talking about here. We've got protons. Now, all protons are the same. This is really important, because what it means is that any particular object that you see around you will be made out of stuff. For instance, this thing here that Apple gives us for this for the Apple for the Apple device, so that we can put anything up on the screen over here. Okay, this particular thing is made out of aluminium, and I would say it's probably, I'd be surprised if it's not pure aluminium, although it may be an alloy of different metals. Okay. All right, but it's made out of, I can see that it's made out of aluminium. I pretty much know what aluminium looks like. And aluminium is one of the elements on the periodic table. In fact, it's number 13. Aluminium has 13 protons. That's what makes it aluminium. Oxygen has 8 protons. That's what makes it oxygen. Nitrogen has 7 protons. That's what makes it nitrogen. Hydrogen has 1 proton. That's what makes it hydrogen. If there were 2 protons there, this would not be hydrogen. It would be helium. And that would go for any of the elements. How could I turn hydrogen into helium? Great. Take hydrogen, give it another proton. Now I have helium. How can I turn helium into hydrogen? Take away a proton. It was helium, it is now hydrogen. Everything works like that in this particular model. I could turn gold into lead, or lead into gold. If I remove 3 protons, I will turn lead into gold. If I add 3 protons, I can turn gold into lead. It's pretty much like that. Whether or not that would be something that would be easy to do and worthwhile, and for instance turning lead into gold, and believe me, people have tried. If the cost was not prohibitive, then this would be something that people would do. But trying to add 3 electrons in a fusion reaction from lead to gold, that would not be a very simple thing to do. So basically what I'm trying to point out is that everything is made out of the same stuff. The difference between one thing and another is simply the amount of it. So the amount of protons, in fact. Okay, none of the others count. Okay, let's have a look at the other things. So all protons are positive charge, so the protons have a charge about them. They will either, if there's 2 of them, they'll reject each other, and if there will be a rejection between each other. And if there are, if there's a negative, then they will be attracted to that. However, there's other forces involved, because straight away, if I was you, I'd be asking the questions if they are. If 2 protons are going to repel each other because they're both positive, then how can they exist in the same atom? That's a very good question. It's a question that's probably beyond this lecture, so it's something that we can get at. Suffice to say, the nucleus contains protons and neutrons, and more than likely these neutrons are what is able to make these protons, if you like, be far enough away from each other, but yet still be close enough to each other to form what's called a mass. There are other things involved, but like I said, well beyond this lecture. Okay, so again, just to reiterate, elements are distinguishable only by the number of these protons. That's what makes one element different from another. That's what makes things, all the things that you see around you, different from each other. Okay? All right, now let's have a look at neutrons. So neutrons, I'm using this green color. All of them are the same as protons, so they're the same size as protons. There's only one element that doesn't have a neutron in its normal state, and that is hydrogen. So hydrogen can have neutrons. That's often called heavy hydrogen. There's deuterium, there's tritium. They can have neutrons. I'll get to that in a minute. Okay, all neutrons are the same. Well, if they're the same as protons, then all neutrons must be the same. That's logical. The same element can have a different number of neutrons. Okay, so we would so the same element, hydrogen, can have either one can have a neutron, so it could have a proton. It could have a proton and a neutron, or it could have a proton and 2 neutrons. And this is the difference between that and that of these elements. These atoms of hydrogen are called isotopes.
Dylan's final period.
Okay, the video's on. Okay. Yep. Okay, that's good. Thanks, Cameron. All right. Okay. Sorry for that. Okay. I'm in a sort of a high traffic area, so it's the only place I could get to do this. So we're getting interrupted every now and then. Please bear with that. Okay, now, what else are we saying? So same elements can have different number of neutrons, and these are called isotopes. So I might just write that down over here. Isotopes. Okay. For instance, the word heavy water, I'm sure you've heard of that. It's used in nuclear power plants, heavy water. And heavy water, for instance, is water that's made out of hydrogen, so 2 hydrogen atoms, 1 oxygen atom. But those hydrogen atoms have neutrons, so they're heavy hydrogen, if you like, and then because that water becomes heavier than normal water, it's called heavy water. Okay, and neutrons have 0 charge. That's important as well. Okay, let's move on to electrons. Electrons, extremely small. Perhaps I'll go on this side. Electrons, extremely small. In fact, very, very, very small compared to the rest of the atom, and we would normally call that a charge. Okay, it has it's negatively. Okay, neutral atoms have equal numbers of electrons as they do protons. So that's another important thing in Bohr's model. Okay, so equal amounts of. So if a neutral element has 8 protons, if it has 8 protons, then it's going to have 8 electrons. And if it doesn't have 8 electrons, we would call that an ion. Okay, so I'll discuss ions later on, but yeah, so it's an atom if it's got the prescribed amount of protons and therefore the right amount of exactly the same amount of electrons, we would call that an atom. And then if it has less electrons or more electrons than it normally would have, then we would call that an ion, I-O-N. Okay, now if it's got less electrons than it should have, it's normally would be referred to as a cation, and if it's got more than it usually has, which gives it an overall negative charge, then we would call that an anion. Okay, we can get into that later, but this particular lecture is about mass, so I'm trying to get you to first of all understand what is stuff made of. This is, mind you, I could go in much deeper than this. However, for this particular video, I'm trying to keep this, pretty straightforward and use as little jargon as I can. Okay. All right. I think that pretty much covers that. So, in summary, everything's made out of atoms, sort of at the basic level. Atoms would have a nucleus. The nucleus contains protons and neutrons, except in the one case of hydrogen where there are no neutrons. Protons are all positively charged. They exist together with neutrons in the nucleus, and electrons will fly around them, and the probability of where they are is pretty high that they would be, for instance, in a given radius. So we have electrons would be in different shells. Excuse me. Okay. Oh, that's okay. You're on the video. Oh, off you go. Okay, so electrons will be in different shells. Okay, so that was my distinguished boss that walked past, and you now know who he is. You probably don't, but anyway, you've seen him. Okay. All right. So that pretty much puts the end to this lecture. What else can I do? Please, in the comments, feel free to ask any questions with regards to this particular model and how it works. Be glad to answer any questions at all. Okay, thank you.